let us wait for 5 more minutes for others to join. So, yeah. Good evening, everyone. So, this is problem solving session for the NPTEL course Computational Fluid Dynamics. So, the course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras, while myself, Hankara Kartiga from the Department of Chemical Engineering, IIT Hyderabad, is handling the live sessions. So, every week we have seen the classes from Saturday 3 p.m. to 5 p.m. So, this is just an additional class to cover the extra few problems. And so yeah, today we are going to have the session from 6 p.m. to 8 p.m. Now we'll start the session. So the course layout by yeah yeah you were saying something.
No, ma'am, go to me, just say.
Okay. Yeah, sure. So yeah, the course layout, we have just seen the calculation of flow in a rectangular duct and triangular duct in the first 2 weeks, and we got a basic idea of how to solve the fluid flow problems computationally by using all the numerical techniques and all. And after that we have seen like what do we do in CFD. we solve the equations numerically. So those equations come from the system, like flow in the system. So those are the governing equations like continuity equation, moment of conservation equation, and if there are additional things happening inside the system like reactions or any heat transfer, we solve those equations as well, like conservation of energy, conservation of like species, everything. So those things equations we saw, and after that incompressible flow equations and boundary conditions we saw in the fourth week. So those boundary conditions are nothing but like we have majorly we have two types, like Dirichlet boundary condition and Newman boundary condition. In Dirichlet boundary conditions, what we do is we give the values for the variables along the boundary, while in Newman boundary conditions we give the values for the derivatives along the boundary. And in week 5 it is about CFD basic concepts like finite difference approximation. There are like very techniques like finite difference approximation, finite volume method, and finite element method. So this one is like basically we just divide the grids according to like I mean it would be in increasing, like based on IJK components we divide the grids, and we use the finite difference techniques like forward difference, backward difference, all those techniques. And after that it was about when we are using that we need to have a confirmation that we would be obtaining the solution at the end of those numerical steps. So for that we need to have some idea whether if we give this condition and if we give this boundary, whether that would be I mean if we give the boundary conditions and if we give these grid size and if this time step, so everything plays a role in getting this stable solutions. So for that we should have an idea. So for that we had like consistency, stability, and convergence, and we also saw Lax theorem. So after that it was about solution for Navier-Stokes equation for compressible flows. So in all these things, all like numerical calculations we do for getting understanding the fluid flow in a domain. So for solving the fluid flow in a domain, we just need to get the solution of Navier-Stokes equations. So in Navier-Stokes equation basically we have various issues like pressure, velocity coupling, and non-linearity of the equations. So those things are like play a major role, that we need to have some sort of strategies or some sort of solution method to get the to solve the system. So we saw first about compressible flow solutions, and later on about incompressible flow solutions of the Navier-Stokes equation. And then last week it was about like last week problems were about linear algebraic equations, basic methods, and advanced methods. We had a brief intro on that and few problems. So this week it is about mostly solving the solution of new algebraic equations using advanced methods. And after that it is about basics of finite volume method including grid generation. And at last we will be finishing with turbulent flows and turbulent modeling. So in today's class we will be solving the problems from week 10 majorly, and few sample problems from week 11 problems. So that is the outline for today's class also. So now let us go on to problems. So assignment problems these are. So we have a domain A, B, C, D, and inside that we have one more small domain of an interest E, F, G, H, and in along AD we have this adiabatic condition where there is no transfer of heat or mass. We will see what it is given in the problem statement. So first it is given that you wish to solve the Poisson equation in a two-dimensional domain shown in figure 10.1. So this is figure 10.1. The rectangular domain EFGH has a constant source per unit area. So EFGH, that is the inside rectangular domain, has a constant source per unit area. Side AD has Newman boundary conditions, while AB, BC, and CD are Dirichlet boundaries. So here it is like AD has a Newman boundary condition because there is no change. We can give that there is no change along the boundary. So in that case we can use Newman boundary condition, that there is no change from this side to that side, change of heat or change of mass. And you use uniform mesh and use a second order accurate discretization of the Poisson equation, and you wish to solve the resulting set of linear algebraic equations which you have expressed in matrix form as Px is equal to Q. For this problem, answer the following questions. So I hope it is clear now. So what are we given? That we have a like we have a figure ABCD and inside that we have a small figure EFGH, and in this, along this line we have Newman boundary condition, and along the rest of the lines we have Dirichlet boundary conditions. And we solve for we use uniform mesh, and we use second order accurate discretization schemes and solve the resulting set of linear algebraic equations. Those equations we have expressed in the form of Px is equal to Q. Like similarly, like we have done in the last class also, like Ax is equal to B format we have rearranged. And for this problem we need to answer the following questions. So okay, first we need to identify the Poisson equation form, because it is given. Solve the Poisson equation in two-dimensional domain. So first we need to know the Poisson equation, how it looks like. So for that we are seeing Poisson equation in a two-dimensional form. So the equation looks like this: dou square f by dou x square plus dou square f by dou y square is equal to c, that is a function of x and y. And later we need it was mentioned that we are using second order accurate discretization schemes. So in that context we are just using central difference scheme and getting the second order accurate discretization. What we are doing, we are first expanding this term along the x direction. So it becomes fi minus 1 comma j minus 2 fi comma j plus fi plus 1 comma j. So here it is moving from I minus 1 to I plus 1. Because we are doing it in the x direction, j remains constant, that is the j location is constant. And this particular term again we are varying from j minus 1 to j plus 1, and ith position we have kept it as constant, and again it is a function of x and y. So I hope this one is okay. So because the question we are asked to solve for the Poisson equation in two-dimensional problem, we have taken this equation: dou square f by dou x square plus dou square f by dou y square is equal to some constant. If it is a Laplace equation, that would have been 0, but here it is a constant. And since in the question it was mentioned that we should be using second order accurate discretization schemes, we are using fi minus 1 comma j minus 2 times of f of I comma j plus f of I plus 1 comma j divided by delta x square plus f I comma j minus 1 minus 2 times of f I comma j plus f I comma j plus 1 divided by delta y square is equal to that constant. I mean, not constant, it is a variable along x and y. So which would be depending on the particular location and particular grids. So let us now see the questions. So in the question 1, it is asked that which of the following methods can be used to solve Px is equal to Q from the above problem. So it is asked that we are, like it was mentioned that we would be rearranging the equations in the form of Px is equal to Q, and we need to solve for the problem. And which of the methods, that is numerical methods, would we be using when we are solving such problems? So the first one is ADI method, second one is ILU method, third one is TDMA method. So ADI is the alternating direction implicit, and ILU is incomplete LU method, that is decomposing into lower and upper triangular matrix, and third one is TDMA, tridiagonal matrix algorithm. So all the methods are like numerical techniques which we use to calculate for the solution, and among these three methods there is a one method that requires a specification, that is TDMA, which requires that it should be having some sort of diagonal structure. Mostly the tridiagonal structure should be maintained in the problem in order to get a solution. But if you remember the problem statement, we can see that it is a Poisson equation. So there is one term in the right hand side, and like there are it would not be like we have 1, 2, 3, 4 and 5 terms, and apart from that there are like inside that is EFGH we had one more domain inside the system, so that was a constant. So it would not be affecting the problem because it has a constant source per unit area, that is the right hand side C in the equation, Poisson equation. Here it would be constant in the EFGH area, but apart from that in the other zones it would be it would not be constant. But then what is it?
I don't understand anything, sir. Ma'am,
Okay.
please, ma'am, assignment 11.
Assignment 11 I'll take tomorrow.
Answer 11.
No, you are talking about assignment 11, right? This one is that one I do tomorrow.
Tomorrow.
Yeah, tomorrow again we have
Assignments.
class 3 to 5.
Solution, ma'am.
Sorry?
Assignment solution 11.
Assignment solution I would not be giving, but similar problems I am taking tomorrow. Like assignment 11 solution, I mean not solution, assignment 11 deadline is not yet over, right?
Not same problem, but similar problem.
Similar problems, that's what. Similar problems I am doing tomorrow's in tomorrow's class for assignment 11.
Okay, ma'am. Thank you.
Yeah, okay. This one is like like mostly 10 assignment 10 and like practice problems from week 11. Okay. So what I was saying is that in this regard, we would not be getting a tridiagonal matrix format. So 1 and 2 would be, we can use it for getting the solution px after rearranging it in the form of px is equal to q. But TDMA algorithm is not feasible for this particular problem, because it requires a specific diagonal structure which is not possible from this system. Like we have Dirichlet boundary conditions, so for every points it is not possible to use all the points, but rather in some areas near the boundaries we would be having less than 5 points, and in some corner points we would be having less than that. So it is not possible to get the tridiagonal matrix structure which we require in the TDMA solution. So we can go with ADI and ILU method. So options given are option A 1 and 2, option B 1 and 3, option C 2 and 3, option D 1, 2 and 3. So option A is the right answer, because we cannot use TDMA algorithm. We can use ADI and ILU method. So that is like iterative things which we can use. Now in question 2, it is asked that which of the following methods cannot be used to solve px is equal to q from the above problem. So you should be careful of the questions. In this it is asked which cannot be used. Since it is cannot is highlighted, we are able to focus on that cannot, but even if it is not there, you should be like carefully reading the questions while doing assignments or even in the exam. Please read the questions twice to get a clarity of what is being asked. Is it can be used or is it cannot be used. So options are 1 SOR method, that is over relaxation successive over relaxation method, and second is multi-grid method, third is SIP method, Stone's implicit procedure. So option A1, that is SOR method, option B 2, that is multi-grid method, option C 3, that is SIP method, option D all the three can be used. So I would go with option D, because all these methods does not pose any restrictions in this particular problem. Like SOR successive over relaxation, we are just using over relaxation factor, and here it is multi-grid method. Again here our geometry does not pose any restriction to it. And third one is Stone's implicit procedure. Again, there is no restriction faced by our particular case with any of these three methods. So right answer to this problem is option D. Option D is the right answer. So we'll go to question 3. In question 3, it is asked that which of the following statements is true about the source term in the region EFGH. First one, it strengthens the diagonal dominance of the discretized equation in the region. it weakens the diagonal dominance of the discretized equation in the region. It affects the column vector Q. And option A 1, option B 2, option C 3, option D 1 and 3. So for option E 2 and 3. So for answering this question, I would say the answer is option 3, that is it affects the column vector Q. So for that we should know that what form we are arranging. We are arranging the equations in the form of Px is equal to Q. So Px is equal to Q, where x is all the discretized points in the domain. So if we go back to the Poisson equation, so this is our domain. We are dividing it into our interest uniform. We are dividing it into a uniform mesh of our interest, and we are getting the solution for the Poisson equation in two-dimensional form. So the equation is this, and here it is the discretized form of the equation. So if EFGH has source term as constant, what is mentioned in the problem statement also, rectangular domain EFGH has a constant source per unit area. So EFGH, this particular zone, has a constant source per unit area. So okay, so constant, this particular thing is constant. So if it is constant, where do you think it would be affecting? It would be affecting the Q, because it becomes constant. The rest of the terms is not being affected. So like these points are what it constitutes the x vector, and the coefficients would be forming the P matrix. So the P matrix has the coefficients, and x column vector has the grid points, and Px is equal to Q. So that particular Q column vector has all the constants in the equation. So it's similar to solving Ax is equal to B. Here we are rearranging it in the form of Px is equal to Q, and in Q we have all the constant values. So if this becomes constant, there is no way in which it affects the diagonal dominance of the system. So it is not strengthening the diagonal dominance, nor it is weakening the diagonal dominance. It is not at all influencing the diagonal dominance, because you can see that it is lying separately. In all other regions apart from the EFGH zone, this particular is a variable, whereas in the EFGH zone it is a constant. So that is what is given. So in the EFGH zone, if it is a constant, it improves, or it adds up the column vector, or it affects the column vector, and that is column vector Q. That is, since we are doing it in the form of Px is equal to Q, so it affects the column vector. So it either increases or decreases the column vector, but it has no, it is in no way affecting the coefficient matrix. So if it is not affecting the coefficient matrix, we cannot say that it is strengthening or weakening the diagonal dominance. It literally has no impact on the diagonal dominance of the discretized equation in the region. So answer is option A 1, option B 2, option C 3, option D 1 and 3, option E 2 and 3. So our right answer is option C is the right answer, because it is falling in the right hand side zone in the equation itself. That particular value is in no way affecting the diagonal dominance, rather it is only increasing or decreasing the column constants. So since the constants all come under the equation, constants fall under the Q vector, we say that it is affecting the column vector. So answer is option C. We go to question 4. In question 4, it is asked that which of the following statements is true about the side EH. So which of the following statements is true about side EH? So we will see the statements first. Dirichlet boundary condition is applicable on EH. Newman boundary condition is applicable on EH. Robin boundary condition is applicable on EH. And no boundary condition is applicable on EH. So the question is regarding which type of boundary conditions can we apply on the side EH. So to identify that, what is, we are given three options like Dirichlet, Newman, Robin boundary conditions. So Dirichlet is nothing but we are giving the constant values, and in Newman, constant values to the variables, and in Newman we give the values of the flex, and Robin, I think it is some sort of combination of Dirichlet and boundary and Dirichlet and Newman, which I'm not sure. That is mixed too, I think, but in Robin boundary condition, but it is a type of boundary condition that I can assure. And last one is no boundary condition. So we need to now identify whether we are applying any boundary condition on EH or not, and if we are applying, what type of boundary condition we are applying. So for that we need to identify EH is a Robin boundary condition is a weighted combination of Dirichlet boundary condition and Newman boundary condition. This is contrast to mixed boundary condition, in which are boundary conditions of different types or specified on different subsets of the boundary. So what do we do in mixed boundary condition? In mixed boundary condition, we in different subsets of the boundaries, we give different type of boundary conditions. Like for till this particular zone, we give Dirichlet, and after that particular region, we give Newman. If that is the case, that we call as mixed boundary condition. But if in the whole entire boundary we give the boundary condition as a combination of Dirichlet and Newman, we say that as a Robin boundary condition. So here the question is about whether we are using any boundary condition on EH, or if we are not at all giving a boundary condition. So for that we need to identify which is the EH zone. So we go back to the question, and this is the EH zone. So for first, let us understand that boundary conditions are those we give to the external boundary to signify anything differently happening across that point. So here we can give a boundary condition because there is no exchange of anything, like that is why it is given as this particular symbol, and here and here. So we can apply boundary conditions like here, here. But this EFGH is a rectangular domain which is a part of the ABCD domain. But only difference it is that it has a different source, where the source is a constant one per unit area. But rather than that, there is no difference between ABCD domain and EFGH domain. Like only the source term is differing. So we should not be applying any boundary condition on this EH point because it is part of the entire domain. It is just a part of the entire domain where the source term is different. But apart from that, it is a part of the domain. So we would not be using any boundary condition. So answer is option D. No boundary condition is applicable on EH. And option D is the right answer. And now let us go to question 5. In question 5, it is asked that which of the following statements is true about SOR method if the coefficient matrix is diagonally dominant. So this question, it is asked that which of the following statements is true about SOR method if the coefficient matrix is diagonally dominant. So first one, its convergence rate increases monotonically with SOR parameter W. Second, it is convergent if W value is between 0 and 2. And third, its convergent rate is twice as much as that of Gauss-Seidel method. Okay. So the question is about SOR method, and if the coefficient they are given, it is diagonally dominant. So it is a comparison between SOR method and Gauss-Seidel method. The statements are looking that way. So the first statement, it is mentioning that the convergence rate in SOR increases monotonically with W. So that is not the case because W value, according to this concept, if we increase the W or omega from 0 to 2, the convergence rate should also increase. But that is not the case, right? it always comes down, depends on the system you are solving and depends on the equation type and so many other factors. So it is not always a direct relation between the convergence rate and the SOR parameter. So if it had been the case that convergence rate is increasing monotonically with W, we can always keep the W at max to get the convergence rate fast, but that is not happening. So first point is false, and second one, it is convergent if it is between 0 and 2. This one is true. So like if the value of W is between 0 and 2, we can say that it can achieve convergence. So that is the main point over in SOR method, successive over relaxation. We can have an assurance of convergence if it is 0 to 2. And third, its convergence rate is twice as much that of Gauss-Seidel method. So again, this is a false statement. Imagine if that is the case, like it is giving results twice as fast of Gauss-Seidel method, then we would always be using the SOR method. So that is not the case. So convergence rate is twice as much as that of Gauss-Seidel method is also false. So right answer is option 2. Option A is 1. Option B, answer is 2. Option C, it is 3. Option D, it is 1 and 3. So right answer is option E again we have, which is 2 and 3. So answer is option C. Okay, option B. Yeah, option B. Like it is convergent if it is 0 to 2. So that is what I was saying. Answer is option B, because the statement which is true is only that if it is between 0 and 2, if W is between 0 and 2, it is convergence. Or in all other cases, it is not convergent at all. I mean, it is doesn't mean that. It means that convergence rate is not directly proportional to the value of W, or it is not as fast as that of the Gauss-Seidel. It is like we cannot put some point onto it. So that is a false statement. Now let us go to question 6. Okay, in question 5 itself we have that as long as the we call it omega or W, whatever it is, omega is between 0 and 2, convergence is assured. So as long as the omega is between 0 and 2, convergence is achieved when you are using SOR method. So what is SOR? It is successive over relaxation. And rate of convergence is varying, which depends on, as before, on the spectral radius of the new iteration matrix. So like rate of convergence varies and it is dependent on the spectral radius of the new iteration matrix as before. And omega varies between 1 and 2 for over relaxation case, but rate of convergence does not vary monotonically between 1 and 2. So again, if it is between 1 and 2, we call it over relaxation, right? But we cannot say that even in that particular zone that there is a monotonic increase of convergence rate from z as we increase the omega from 1 to 2. That is, if I achieve convergence in 1 second, I mean if the omega is 1, if I say that I achieve the convergence in 1 second, and if I say that I increase the value of omega to 2, I should get the convergence in at least half the time, like linear relation or some in reduced time. But like that in more way, if omega is 1 and 1.5 and 2, and for rate of convergence it should be like 2 seconds and again 1.5 seconds and 1 second. If that is the case, we can say that the rate of convergence is varying monotonically between 1 and 2. But here in successive over relaxation, it is mentioned that it is not the case. That is, as we increase the omega from 1 to 2, there is no trend. The rate of convergence does not vary monotonically between 1 and 2. So that is the question 5. It is convergent if it is between 0 and 2. In all other options, it is not right. Let us go to question 6. Okay. Typically, it goes through a minimum or the number of iterations needed to reduce the residual by a factor of 10. That value is asymptotically convergence rate. It reduces as omega is increased, it goes to a minimum and then it starts coming back up. So that means there is an optimum value of omega for a given matrix and for a given SOR method. This optimum value will have the least number of iteration steps and needed to reduce the residual factor of 10 by residual by factor of 10 and have a high convergence rate. So what it means is that uh, like it would be going like this, like it would be, let us say that this is omega and this is convergence rate. So it goes through a minimum. So here, from here it is decreasing and then it is increasing. So it goes through a minimum or the number of iterations needed to reduce the residual by a factor of 10. So that is asymptotically convergence rate. As omega is decreased, it goes to a minimum and then it starts coming up. So there is an optimum value of omega for a given matrix and for a given SOR method. So that optimum only will have the least number of iteration steps needed to reduce the residual by a factor of 10. So like here the convergence rate is 2 seconds or something, here it is 1 second. So here this one is the optimum value of omega. So you can see that after that optimum value of omega, again the number of iterations, rather than saying convergence, I can say number of iteration step, number of this iteration step, number of iteration step is what is coming here. So number of iteration steps is very low for this particular omega. After that again it is starting to increase. So this optimum value will have the least number of iteration steps needed to reduce the residual by a factor of 10, and that point will have the highest convergence rate. So at this we can say that it is a optimal omega, and this point it will have the least number of iteration steps required for reducing the residual by a factor of 10. So that is SOR method. Now we go to question 6. In question 6 it is asked that in comparison with the Gauss-Seidel method, number of floating point operations required one iterative step of going from xk to xk plus 1 using the SOR method. So in comparison with the Gauss-Seidel method, number of floating point operations required for one iterative step of going from xk to xk plus 1 using SOR method is option A far more, option B twice as many, option C about the same, option D far fewer. So in this question it is a comparison between Gauss-Seidel method and SOR method. So in Gauss-Seidel method, when we are going from xk to xk plus 1. Similarly in SOR method we are going from xk to xk plus 1. K is nothing but the iteration step, like it is kth iteration to k plus 1th iteration. So as we go from x at kth iteration to x at k plus 1th iteration, the number of floating point operations required for one iterative step, that is k to k plus 1th iteration step, how does it vary between Gauss-Seidel and SOR method? So is it more in SOR method, or is it twice as many, or is it about the same, or is it far fewer? I would say that it is not about the total, but it is a floating point operation between requiring from one time step to another time step. So it is a floating point operation, so the mathematical calculation being performed. So there is no difference, like only extra factor is getting in the equation, but rather than that there is no major difference. So the number of floating point operations required for one iterative step remains the same. That is, it is about the same as the right answer, because Gauss-Seidel method and SOR method, there is only one additional factor in the SOR method, that is omega. But apart from that omega, we do not have any major operations which is like differing. So we can say that number of floating point operations required for one iterative step of going from xk to xk plus 1 is the same between Gauss-Seidel method and SOR method. So right answer is option C. Option C is the right answer. Now let us go on to question 7. In question 7, it is asked that in the ADI method for the solution of AX is equal to B is based on the decomposition of. So ADI method, that is alternating direction implicit method, which we use to get the solution for AX is equal to B, is the based on the decomposition of what? Option 1, matrix A into m plus 1 n. Matrix A, here we are decomposing into m plus nth matrix, and second option, it is matrix A the problem is being divided into two tridiagonal matrix problems, and option C, matrix A is appropriately matrix A approximately into LU, none of the above. So ADA is nothing but alternating direction implicit method. In the numerical techniques, this ADA is an iterative method, and it is very popular while solving the large matrix equation. Like when we are using PDEs, it is widely used for solving parabolic partial differential equations and elliptic type partial differential equations. So it is majorly used for modeling heat conduction and diffusion equations. So like heat transfer is there and mass transfer is there in either two-dimensional problem or in three-dimensional problem, whatever it is. So here it is a two-step iterative process. It splits the matrix into an approximate solution, and there is like two-step iterative process, and here we are dividing it into two tridiagonal matrix problem. So answer is option B is the right answer, where we are dividing the problem into two tridiagonal matrix problem. So how is it we are doing? In numerical linear algebra, alternating direction implicit method is an iterative method which we use to solve for the matrix equations. So it takes advantage of the goodness of tridiagonal matrix algorithm. So for tridiagonal matrix algorithm, we use it. It has the advantage like getting solution faster. So this ADA method uses this advantage and decomposes the solution, decomposes the system into two tridiagonal matrix, and therefore this scheme is therefore expected to have a faster convergence than the Gauss-Seidel method. But it is not as fast as optimal SOR method. As you all know that in optimal SOR method, we had a curve, right? Like number of iterations versus omega, we had a curve at which omega point we have the least number of iterations. So if we use that omega value, we will be having the least number of iterations. So that is the optimal method. This ADA method is faster than Gauss-Seidel method. That it is a normal. It is faster than normal iterative technique method, but it is not as fast as the optimal SOR method, because in optimal SOR method we are made sure that we get the solution with least number of iterations. So therefore, if we take Ax is equal to B, so like what we saw in the domain, we are discretizing the equation in the form of Ax is equal to B, and then decompose it into A into A1 plus A2. So we are decomposing the coefficient matrix into two components, A1 plus A2, and we are putting it in a particular format, that is 1 plus tau 1 A1 into x at n plus half time step is equal to 1 minus tau 1 A2 into x at nth time step plus tau 1 B. So here we are calculating at n plus 1 half time step, and after that we are going to n plus 1th time step. So rather than jumping from n to n plus 1th time step, here we are having an intermediate point, that is n plus half. And we are dividing the A matrix, that is the coefficient matrix, into two matrix A1 and A2, and putting it in a particular form. And after that we are having two equations, as we said. Like one more equation is in the form of 1 plus tau 2 into A1 into xn plus 1 is equal to 1 minus tau to a2 into x n plus half plus tau to b. So what are we doing? We are just decomposing the matrix Ax is equal to B into two matrices. I mean decomposing the coefficient matrix into two matrices A1 and A2, and we are rearranging the original equation into putting it in this particular format. 1 plus tau 1 A1 into x at n plus half is equal to 1 minus tau 1 A2 into x n plus tau 1 B, and one more equation is 1 plus tau 2 A1 into x at n plus 1 is equal to 1 minus tau 2 a2 into x at n plus half plus tau 2 b. So this is n plus half, n plus 1, right? And after that a2 is part of it is being evaluated explicitly and a1 part of it is being evaluated implicitly. So after that we'll be getting the solution, but this a1 and a2 are like two tridiagonal matrices. So in that, from the question asked, it was about ADA method for the solution of Ax is equal to B is based on the decomposition of A matrix into A1 and A2 matrix, and it is so therefore we are saying that the problem is divided into two tridiagonal matrix problem. I hope it is clear. Now we'll go to question 8. In question 8 it is asked that in the SIP method, Stone's implicit procedure method, for the solution of Ax is equal to B, matrix A is decomposed into. So in the previous method, that is ADA method or alternating direction implicit procedure method, what we did, we have divided the problem into two tridiagonal problems. That is A, we have decomposed it into two matrices A1 and A2. So in a similar way, SIP method is nothing but Stone's implicit procedure. What are we doing? So in the SIP method for the solution of Ax is equal to B, matrix A is decomposed into option A, LU, that is lower and upper diagonal matrix, triangular matrix, and ILU, that is incomplete lower and upper matrix, and LU plus N, and option D, none of the above. So right answer to this problem is LU plus N, that is we are dividing the SI matrices, matrix A, that is matrix A is nothing but the coefficient matrix. So this is what we are just a minute. I mean Ax is the grid, x is the grid points and A is the coefficient matrix for which we get the coefficients of the grids when we decompose the equation. So after rearranging it in the form of Ax is equal to B, if we use SIP method, that is Stone's implicit procedure, Stone's method, or not Stone's, sorry, it is a Stone's method and it is known as strongly implicit procedure. Strongly implicit procedure or Stone's method. Till now I have been saying it as Stone's implicit procedure, that is wrong. Just forget it. It is strongly implicit procedure or Stone's method. So it is an strongly implicit procedure. It is an algorithm for solving a linear sparse linear system of equation. So again it uses iterative solution. So I would say that it is option C is the right answer. So here we are just decomposing the matrix into LU, and additionally some N also comes into picture, like incomplete one. So answer C is the right answer. Option C is the right answer. That is, Stone in 1968 proposed an ILU method which is more implicit than conventional ILU. So we can say that it is an ILU method, but it is more implicit than ILU. So it is, rather than splitting them, having an incomplete LU procedure, Stone proposes strongly implicit procedure, that it is more implicit than the conventional ILU, and we are able to get a solution. So in 1968 he proposed a more implicit ILU procedure, that is more ILU. So we can say that it is LU plus N. So option C is the right answer. Now let us look at question 9. In question 9, it is asked that which of the following statements is true about the multigrid method of solving Ax is equal to B. So as we have seen that we have an equation, we have a system where we have discretized the system into grids by using discretization schemes like forward difference, backward difference, or central differencing schemes, and we get the equations. So after that we are just rearranging the terms, and we are getting a coefficient matrix and the grid points in the X matrix and constants in the B column vector. So after that, which of the following statements is true about the multigrid method of solving Ax is equal to B? Option 1, it uses several grids for the same computational domain. Option 2, it solves the same equations on all the grids. It uses the same boundary condition on all the grids. So the first statement, what is saying, it uses several grids for the same computational domain. Yeah. What is multigrid method? We just go from the coarser to grid to the finer coarser grid to the finer grids to the coarser grids, so we reduce the errors. I'll explain from which order we go in the next slide, but we go from one grid to another grid to reduce the errors. So we have uses several grids. I'll just explain that more detail in the next slide. And second one, it solves the same equations on all the grids. Not exactly the same equations. Since we are just modifying the equation to get the proper error form, or reducing the error, so we can't say that it is the same equations, but the boundary condition remains the same. So it uses the same boundary conditions on all the grids. So I would say that 1 and 3 are the right answer. We'll look at the options first. Option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So accordingly, if we choose the option 1 and 3 is mentioned in option C. So our answer is option C. So now let us look at how option C is the right answer. So for that we need to know what is multigrid approach. So in multigrid method, it is a numerical technique. It is an algorithm for solving differential equation using a hierarchy of discretization. As I've said, we have a hierarchy of discretization going from one grid size to the other, and they are very useful in problems exhibiting multiple scales of behavior. For example, many relaxation methods exhibit different rates of convergence for short and long wavelength components, suggesting that these different scales be treated differently. So what happens that in the equation, different components will be there, like short wavelength components and long wavelength components. So depending on the wavelength components, the rate of convergence and errors would be different. So rather than treating all of them in the same grid size, if we go from one grid size to the other, we can have a better convergence rate and better reduction in the error. So we are treating those scales differently, and the main idea of multigrid method is to accelerate the convergence of a basic iterative method known as relaxation, which generally reduces short wavelength error by a global correction of fine grid solution approximation from time to time, accomplished by solving a coarse problem. The coarse problem, while cheaper to solve, is similar to that fine grid problem in that it also has a short and long wavelength errors. It can also be solved by a combination of relaxation and appeal to still coarser grids. So we go from finer grids to coarser grids, and thereby in the finer grid we have reduced the short wavelength errors, and after going to the coarser grids we reduce the longer wavelength errors. So in a series of grids, we go from reducing the short wavelength error to longer wavelength error and the longest wavelength errors, and after that the solutions pass on to the finest grid, and it continues. So this is the basic principle behind the multigrid method, and just that it is an algorithm for solving differential equation using a hierarchy of discretizations, and it is useful in problems exhibiting multiple scales of behavior. For example, many basic relaxation methods exhibit different rates of convergence for short and long wavelength components, and we are treating them differently. So, in a more understanding way, how can we say that in an iterative method, what is our objective in any iterative method? It is to reduce the residual. Residual is nothing but those difference between the what we get and what we expect. Our objective is to get the residual. Degree of non-satisfaction of the current solution with respect to that of the original governing equation Ax is equal to B, arising because of some error in the solution. So our aim is to reduce the residual. So that too, what is residual? Residual, we can say that it is the dissatisfaction of the non-satisfaction or dissatisfaction of the current solution with respect to that of the original governing equation Ax is equal to B, and that dissatisfaction arises because of some errors in the solution, and if we reduce those errors, we can say that we can reduce the residuals, right? So this error can be of varying components, like short wavelength component, long wavelength components, whatever it be. And Gauss-Seidel method, like for example, is maybe good at reducing the error at a smaller scale, and some other methods which are not so effective in reducing the errors. So that error in Gauss-Seidel, uh, smallest wavelength error would be reduced fast, but the larger wavelength errors are not so damped easily. So we go from a series of grids that in larger wavelength errors would be damped quickly. So in multi-grid method, computation starts in the finer grid with few number of iterations, maybe 5 to 10 iterations, and then the error is taken from finer grid to the next coarser grid, and where some more iterations will be performed and some long wavelength errors would be damped out quickly. Then it is taken to the next even coarser grid, so that the middle coarser grid, which was not dampening the middle error, that error will be reduced in the next coarser grid, and it continues. After that, from the coarsest grid, uh, the error would be reduced, and it is then taken to improve the solution of the final grid, and then some more calculations are performed. In each grid, only few calculations, a few iterations are done. So that is the principle behind the multi-grid method. So now looking at the question, when what is true when we are solving for the Ax is equal to B, in Ax is equal to B, it uses several grids that we have seen. We are going from final grid to the coarser grid, and for the same computational domain, it solves the same equation on all the grids. The error is varying, so we can from each grids, so we cannot say that the equation is the same. It would be like it would not be the same. And third is it uses the same boundary conditions on the grids. Boundary condition however remains the same. So 1 and 3 are the right answer, which is correctly given by option C. So answer to this problem is option C is the right answer. So I hope it is clear about multi-grid method. So yeah, that is one. One more. Yeah, multi-grid method is now clear. Let us now take a 5 minutes break, and time is now 7. We will come back at 7:05 sharp. You want to say something?
Yes, ma'am.
What is it?
Actually, my marks of 10, 1 to 9 assignment less than 40%.
Okay.
Then when I appear in a NPTEL exam, and will I fail maybe or pass? Because criteria less than 40%, Oh, there are two criteria passing marks. Above 40% assignment and online exam
Uh,
50%.
yeah. Uh-huh.
So will I fail, ma'am? Because assignment.
Actually, I didn't understand your question correctly.
Ma'am, actually my mark of 10, 1 to 9 assignment less than 40%.
Okay, okay. Yeah.
And passing criteria is above 40%.
Okay, so you want to make up in the final assignments?
Yes, ma'am. 11 and 12.
11 and 12. Okay. 11 and 12, what I would suggest is tomorrow I'll be solving for the sample problems and I would not be touching the theory problems. So for that, you need to watch the lectures. However, like problematic questions, like solving questions, I would be solving a similar problem. So if you can listen that and get an idea, I'm 100% sure you would be able to solve the ones provided in the assignment also. Like mostly similar questions are only being said. Um, like, I mean, if you once see the questions, assignment questions today, and come back tomorrow, like if even after the session, if you are not having any clarity, you can ask. I'll help you. Like, I mean, I would not be giving the solution, but I can guide you in direction.
Can you give me solution, ma'am?
Solution I can't give, right?
Why, ma'am?
That is not part of our work. But
Answer, ma'am.
I can help you with how to solve those.
60%, ma'am.
See that, like a direct solutions I can't give you.
Answer, ma'am.
Answer only illa. That's
Only
what I'm
answer.
saying. See, I can give sample problems which would definitely help you in solving those. Like that would up. I'm saying apart from the sample problems, what you will be left out with is like theory questions, like understanding ones. So that would be simple ones which you can solve directly. Like what is, if you look at the course layout, yeah, it is like finite volume method and grid generation. Week 11 is like you can do it. It will be like structured mesh and unstructured mesh and problems related to that. So like like what I can say is I would not be solving the taking the exact domain and solving, but similar domain I am taking for the tomorrow class, like, similar to the one in this week's assignment, and on that basis, like to be more precise, like the system we are taking is different, but the questions that can be asked from us, like I mean, questions that can be asked is like same. So that would be helpful, like if you can see that you can score more marks in tomorrow, I mean in week 11 and 12.
Not sure, ma'am. Pass it.
You can do it, bro, no issues. Like you can, the little more effort you can do it. In fact, you can do it very well, like, yeah. like similar questions are only there in the next class also. So I'll give an introduction also today, so just look at it and we can do it tomorrow. So yeah, now let us continue. In question 10, it is about multigrid method is efficient in solving Ax is equal to B because option 1, only part of the computations are solved on the grid. Option 2, computation on coarser grids takes lesser computational time. Third, computation on coarser grids takes few iterations to converge. So okay, and the question is about why multigrid method is efficient. We are saying the multigrid method is efficient at reducing the errors, and like multigrid method is preferred than going with the same grids. So why is it efficient in solving Ax is equal to B? I mean, why is it efficient? Is it because only part of the computations are solved on the grid, or computation on coarser grid takes lesser computational time, and computation on coarser grids takes few iterations to converge? So options are option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So our answer is option D, because we have seen what multigrid method is. So on that basis, what we can say is that uh, we are going from finest grid to coarsest grid. So in each grid size, we are doing a part of the calculation, or we are doing a part of the error reduction, more to say. So we can say that only part of the computation is solved on the grids, and second one, computation on coarser grids takes lesser computational time. So we all know that in coarser grids, what will happen? We like, since the grids are coarser, we can transfer the information very fastly from one grid to the other. So the computation time required is lesser there, because we are transferring the information faster. The total computational time is less. Third one, computation on coarser grids takes few iterations to converge. Like in the finest grid, like there would be more errors, and after that, once we have moved on to coarser grids, with few iterations we can get the converged solutions. That is the theory behind this, that we are going from finest grid to coarser more coarser to the coarsest grids. So thereby we are having a reduction in computational time as we move to coarser grids, and iteration numbers are also reduced as we go to the coarser grids. So we can say that part of the computation are solved on the grid, as well as computation on coarser grids takes lesser computation time and less few number of iterations to converge. So our right answer is option D is the right answer. Let us now move on to question 11. Not 11. So this is week 11's non-graded assignment problems, or just practice problems for you. So we have two grids. So the week 11 is about finite volume method and grid generation. So if we say grid generation, two things come, like one is structured grid and another one is unstructured grid. So we have one grid over here and the other grid over here. That is, one grid is actually missing. Okay, yeah, here it is B. We have one grid, two grid and third grid. So I would say that it is B is an unstructured grid, because you can see that it is not having any like directions in which it is increasing or decreasing or whatever it is happening. It is just random placement of randomly generated grids. So we can say that option B is an unstructured grid, but we will just look at the questions now and we will discuss the answer. So question 1, it is about, with reference to figure 1, which of the grids can be considered as a structured grid? figure 1a, figure 1b and figure 1c. So those are given in 1, 2 and 3 options. So after this we'll get the options where we need to choose which of the grids can be considered as a structured grid. Option A 1 and 2, option B 2 and 3, option C 1 and 3, option D 1, 2 and 3. So B is an unstructured grid. So answer should be option C. Yeah, answer is option C. That is 1 and 3 are what we consider as structured grid. So we go back and look at the grids one more time and identify which is a structured grid and which is an unstructured grid, or whatever it is we call it, but we'll go back and look at it. So we have like structured grids or unstructured grids or whatever. Um, Here we can say that it is like there is some sort of structure, like it is going from here to there and it is getting divided over this, so we call it as a structured grid. But in this particular figure 1b, if we look at it, there is randomly generated triangles across the domain. The grid placement is not in any structured way. That here we can say that it is along this line the grids are divided, but that format we are not able to say here, like it is like this and here it is like that. At least if it had been like this, we can say that it is a structured grid in some way, but again here we are dividing it. There is some unstructuredness over here, but that is in option C. Again it is a uniform and it is not an unstructured grid, it is again a structured grid. So in mostly in unstructured grids, we cannot use finite difference approach. So we would be using finite volume approach mostly. So according to that, we have figure 1. With reference to figure 1, which of the grids can be considered as a structured grid? So option 1, 1 is 1a, 2 is 1b, 3 is 1c. So options 1 and 2, 2 and 3, 1 and 3, 1, 2 and 3. So the right answer is option C, that is 1 and 3 is the right answer. Option C is the right answer. Now let us look at question 2. Okay. So okay, this is for our understanding. Here we call it as a structured grid because there is some structure arrangement. But in unstructured grid, we can see that here, like although here in this region it looks like structured, along the walls if you look at it, here in this zone they all look like unstructured mesh. Structured mesh means volume elements are well ordered. That is what I am saying. If we call each as volume element, they are in well ordered arrangement, and a simple scheme can be used to label elements and identify neighbors. That is, we can see that it is first cell, second cell, right? So here I can say that this is ijk and here it is ijk or I plus 1 jk, something I can mention. But if you look at it in this particular domain, I cannot say this is ijk and here it would be different, here it would be different, everything is different. Even though I cannot even say it as I plus some x into j, I mean x, I plus 1 or 1 times of k, 2 times of k, n into k, not k, I mean what I mean is x plus or I plus 2 times of x plus 1i or x plus 2i or x plus ni, something in that format I cannot give in unstructured mesh. So a structured grid means that volume elements are well arranged. As you can see here, it is volume elements are well arranged or well ordered, and a simple scheme like ijk indices can be used to label elements. So I can label this element and identify the neighbor from that. So the neighbor is I plus 1th cell, j plus 1th cell, like that I can identify the neighboring elements also. In unstructured grids, volume elements can be joined in any manner. So here you can see that it is joined in some different manner. So here it is like a different manner, and special list must be kept to identify neighbors. So here I can say that I plus 1 cell is a neighbor cell, but here I cannot say that I need to identify which is a neighbor by through any other special means. So I need to have a special list kept to identify the neighbors. So on that basis, again if you look at it, I can say that I plus 1 is ith cell, and here also I can say I plus 1 or j plus 1 or whatever it is, but I can identify the neighbors through some indices. But here if you see I plus 1 or here, okay, here let us keep I plus 1. Here it is sort of confusing which is a neighbor elements. So rather than keeping some indices form, we need to keep an special list to identify the neighbors when we are dealing using unstructured mesh. So that is unstructured grids. So here are few more examples. Here you can see that it is a sphere. So here again we can see that through some means we can identify the neighbor cells from the current cell, but here if you look at it, it is an unstructured mesh. So like from one point we cannot identify the neighbors through some means. Same way here it is a structured arrangement, here it is an unstructured arrangement. Like structured mesh is that volume elements are well ordered and a simple scheme can be used to label elements and identify the neighbors. Whereas in unstructured grids, volume elements can be joined in any manner and we must keep a special list to be identifying the neighboring elements. Now we go to question 2. In question 2, for the solution of Navier-Stokes equation in irregular geometries, which of the following grids can be used? So the question is, ultimately our aim is to solve for the Navier-Stokes equations in the computational domain. So for getting the solution of Navier-Stokes equations, if it is a regular geometry, there will be no issues. But if it is a irregular geometry, what type of grids can we use? That is a concern. So first one is Cartesian grids, second one is structured grids, third one is unstructured grids. So Cartesian grids are nothing but we have definite arrangement like x is x plus some ni, y plus nj and z plus nk, something like that. In xyz we arrange, gridded, meshed, whatever. And in structured and unstructured grids we have seen in prior slides how the grids would look like. For irregular geometries, it is not possible to get the Cartesian grids, right? It is not possible to equally or uniformly mesh using Cartesian grids. So Cartesian grids is not possible. Second one is structured grids. We can use structured grids. In the previous slides also we have seen that we had a rectangular domain or we had a spherical domain. Getting a structured grids is a difficult task comparatively. We cannot get it for all geometries, all irregular geometries. Like it is difficult to get a structured grids while we are dealing with irregular geometries. But it is not impossible. So structured grids is feasible, and unstructured grids we have seen that it is possible and it is mostly used when we are dealing with irregular geometries. So for the solution of Navier-Stokes equations in irregular geometries, which of the following grids can be used? So the right answer is 2 and 3. Options, let us look at the options. Option A 1 and 2, option B 2 and 3, option C 1, 2 and 3, option D only 3. So right answer is option B. Option B is the right answer because we cannot use Cartesian grids, but rather we can use structured grids or unstructured grids. So for irregular geometries, structured grids and unstructured grids are better suited than Cartesian grids for solving Navier-Stokes equations. Cartesian grids are regular grids that are well suited for simple geometries like squares, rectangles, cubes, They become inefficient and difficult to use for irregular geometries because they can lead to a lot of wasted cells in areas where the grid does not conform to the shape of the object. So we are not able to conform to the shape of the object, so it leads to wastage of cells. And structured grids are also regular grids, but they can be deformed or stretched. So as you have seen in the first slide, this we call it as a structured grid, but you can see that it is like we have stretched it here, and here it is shrunken. So it can be stretched or shrunken or whatever be done, but it is having a some sort of structure. But it is a regular grids, but they can be deformed or stretched to fit around complex geometry. So depending on the complexity of the geometry, we are deforming or stretching the cell to suit it. This makes them more versatile than the Cartesian grids for irregular geometries. Unstructured grids are most flexible type of grid and can be used to conform to any geometry no matter how complex it is. They are particularly useful for problems with intricate features or moving boundaries. So these are the things. So according to our question, interest in irregular geometries, we can go with either structured grids or unstructured grids. So option C is the right, or no, not C, B is the right answer because it is dealing with option 2 and 3. So just give me 2 minutes break and I'll come back here. So in question 3, it is about which of the following can be claimed as advantage of an unstructured grid method of solution over a structured grid solution. So the question is, which of the following can be claimed as an advantage of an unstructured grid method of solution over a structured grid solution? So why do we go with unstructured grid when rather than a unstructured grid rather than a structured grid? So in which cases it is advantageous? First one, ease of grid generation. Second one, ease of grid refinement. Third one, ease of solution of discretized equations. Option 1 and 2. Option A, it is 1 and 2. Option B, it is 2 and 3. Option C, it is 1, 2 and 3. Option D, only 3. Our answer is option A because when we are dealing with unstructured grid, as we have seen before, we can easily suit it according to our interest in the complex geometry. Like depending on the geometry, we can just change it according to the geometry, and we can make the ease of grid generation. grid generation would be easier than when we are dealing with unstructured grids. And also grid refinement is made more easier because in structured grid, like we cannot, we need to think of so many things to make it look structured that we cannot, along the walls most of the time we require more finer grids. So in those places it is not always possible to use this structured method to get refined in the particular zone of our interest. So we can go with unstructured grids because we have ease of grid refinement. And so, like, what are the advantages of unstructured grid solution? Option A, grid density can be controlled in any region without worrying much about the density getting increased in the another region. So in structured grid there is a problem that if we are controlling the density in any region, we need not worry about the density. We should be worrying about the density getting changed in the another region when we are using structured grid. But in unstructured grid, we can control the grid density in one region without it affecting us in any way that the other region would be affecting too. Like we can do it region by region, so it is not an issue. And easy to use with complex geometries, can be computed within an hour. Like for complex geometries, using an unstructured grid is better, but uh, using a structured grid is kind of complex, we can say. Why would, because when we are dealing with complex geometries, to get a structured grid, it takes lot of time and lot of effort to get that structured grids. But once we get this structured grid, it is easier to solve. But when we are using complex geometries, it is not easy to use it is not easy to use the structured grid. Easy to get the structured grid, but with complex geometries we can get an unstructured grid easily. And we need not worry much about skewness or bad quality, since the grid generation algorithm takes care of that most of the time when we are using unstructured grids. But in structured grid we need to take care of that as well. So that is the advantage of unstructured grids, because it has ease of grid generation and it has ease of grid refinement in the zone of our interest. Like we need not worry about other zones when we are concerning with this as well. And in third one, it is ease of solution of discretized equations. But we are not getting a in unstructured grids, it becomes difficult to get solution because in structured grid calculations would be comparatively easier in structured grid than in the unstructured grids. So because of that, the getting solution is bit difficult in unstructured grids. In unstructured grids, getting a solution is comparatively difficult than the structured grids. So answer is option A, 1 and 2. Ease of grid generation and ease of grid refinement. So we will go to question 4. In question 4, which of the following statements is not true when we use a structured grid for flow through a complex geometry? So again we have to look at the question very well. It is asked that which of the following is not true when we use a structured grid for flow through complex geometries. Option 1, body fitted grids can be used for only two-dimensional geometries. Option 2, finite difference techniques cannot be used. Option 3, diagonal dominance condition of the coefficient matrix is preserved. I would say all three. So first one, let us see. Body fitted grids can be used only in two-dimensional geometries. It is a false, because it is like conforming the grid according to the shape of the geometry. So it can be used in two-dimensional problem as well as in three-dimensional problem. So it is a false statement that when we say that body fitted grids can only be used for two-dimensional geometries. Second one, finite difference techniques cannot be used. Again, this is false. Like when we use a structured grid, we can use finite difference technique. But when we use unstructured grid, we cannot use finite difference technique. So we should go with finite volume approach. But since we are using a structured grid for flow through a complex geometry, even though the geometry is complex over here, since the grid is structured grid, we can go with finite difference techniques. So again, this statement is a false statement. And third one, diagonal dominance condition of the coefficient matrix is preserved. So it is saying that diagonal dominance condition of the coefficient matrix is preserved when we use structured grid, but we cannot say that. It finally depends on the geometry, it finally depends on the flow domain and what system we are dealing with, everything plays a role. So we cannot say that only a structured grid would lead to a diagonal dominance condition preservation. It is not true. So all three statements are wrong. So we say, we look at the options. Option A only 3, option B 1 and 2, option C 2 and 3, option D 1, 2 and 3. So answer is option D. All three statements are wrong. That is what we mean here. That is, all three statements are not true. All three statements are false. That body weighted. What is the true statements? Counter of these statements are true. That is, body fitted approach grids can be used for three-dimensional geometries as well. Finite difference techniques can be used, and diagonal dominance condition of the coefficient matrix is or is not preserved. It may or may not be. It doesn't come under this. We cannot say that statement as a true statement. Is not true is the right one. So let us go to last question of this today's session. Body fitted grids can be used only with two-dimensional geometry. This statement is incorrect. Body fitted grids, also known as conformal grids, can be applied to complex geometries in both 2 and 3 dimensions. They are particularly useful for such geometries because they conform to the shape of the object, allowing for more accurate representation of the flow. Second one, finite difference techniques cannot be used. This statement is also incorrect. Finite difference techniques are one of the most common methods for solving computational fluid dynamics problems. They can be used with structured grids, including body fitted grids, to discretize the governing equation of the fluid flow. Finite difference techniques are one of the most common methods for solving computational fluid dynamics problems. They can be used with structured grids, including body fitted grids, to discretize the governing equations of fluid flow. Diagonal dominance condition of the coefficient matrix is preserved. So this statement depends on the specific grid generation technique used. In some cases, diagonal dominant conditions may not be preserved when using a body fitted grid. However, there are techniques to improve the diagonality of the coefficient matrix, which can help to ensure the convergence of the finite difference solution. So what we are saying is that there are techniques to improve the diagonality, but we cannot ensure it always. So all three statements are false, and we have seen when it is false and when it can be true. So yeah, why these statements are incorrect we have seen in explanation, and we'll go to last problem of today's session. In question 5, it was asked that which of the following statements is true about the transformation of Laplace equation into non-orthogonal curvilinear coordinate system. Option 1, elliptic equation remains elliptic. Elliptic equation becomes parabolic. Elliptic equation becomes hyperbolic. Parabolic equation remains parabolic. First one, option 1. Second one, option 2. Third one, option 3. Fourth one, option 4. So first thing we need to see is Laplace equation is an elliptic equation. So it is not a parabolic equation, so we can neglect the fourth statement completely, because it is stating parabolic equation remains parabolic. So to begin with itself, the equation is not parabolic, so we can neglect the fourth statement. So we have three statements left. Either it remains elliptic, or it becomes parabolic, or hyperbolic. And first one, it is elliptic equation remains elliptic. It is the case because even though we are transforming the Laplace equation into a non-orthogonal curvilinear coordinate system, the nature of the equation does not change over here. So the elliptic equation remains elliptic. So first one is the right statement, that is option A is the right answer. Option 2 and 3 that is given by option B and C are false. That is, elliptic does not become parabolic or elliptic does not become hyperbolic. So both the statements are false. Option A is the right answer. So why in mathematics a second order partial differential equation is called elliptic, parabolic or hyperbolic depending on the characteristics of the solutions, so which we have seen in previous classes itself. So elliptic equations typically describe steady state phenomena, while parabolic equation typically describe diffusion process. Hyperbolic equation describe wave propagation. When Laplace equation is transformed into a non-orthogonal curvilinear coordinate system, it remains an elliptic equation. This means the nature of the equation and type of solution it produces are preserved under the transformation. So yeah, that's it for this week's problem. We have the class again at 3 p.m. to 5 p.m. tomorrow evening. So we'll meet then and discuss week 11's problems, some more problems. See, these 5 problems are just practice problems, so we'll see similar assignment problems tomorrow class. So yeah, that's it. If you have any questions, you can ask now, from like any questions from today's class or whatever, we can discuss. Time is there, we can discuss now. Yeah.
Final exam, ma'am.
Huh.
Will assignment question will come from?
It may come like.
Ma'am, assignment question come from final exam, ma'am.
Some questions can come. No, I cannot say that all questions will come, but some questions can come, or similar questions can only come. Like, it would not be too different if you can solve the questions.
Thank you, ma'am.
Okay. Like, you practice all the assignment problems from 12 weeks and you will get a clarity, you can do well in the final exam.
Can you give me one number, ma'am?
Can you give?
One number.
I didn't get you. What?
Can you give me one number, ma'am?
No. Like, if you have any doubts, these videos are posted in YouTube. You can mention there, I can help you. Yeah. Thank you. Yes, thank you guys. Thank you for attending. We will see tomorrow. Yeah. I'll close the session very shortly. Yeah, I'll just be back. Yes, I'll close today's session. Thank you guys for attending. We'll meet tomorrow again.